Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning platform. My name is Okeibuno, and the subject we are considering right now is mathematics. And under mathematics, we will be looking at the topic sets, or what you know as the set theory. Under set, we will be considering these subtopics: definitions, relationship between sets, definitions, types of sets, relationship between sets, universal sets, difference of sets, and then we'll finally look at Venn diagrams. Of course, in definitions, first of all, we'll begin with set. What is a set? A set is a well-defined collection of items, a well-defined collection of objects, a well-defined collection, okay, that is talking about items that are together. There is something that is particular, or that is that defines these items and then collects them together under a particular heading. For instance, I can say a set of prime numbers under 20, or a set of prime numbers between 1 and 20. I can say a set of boys, or a set of students in your class, a set of students in SS1, a set of students in SS2, a set of fishes in River Niger, a set of food items in Mr. John's stall, you know. So there is a well-defined collection of that items. There is a boundary, okay, within which those items are situated or collected. That's what we call a set. Now the next thing is the elements of a set. What are the elements of a set? The elements of a set are those items that are in that set. For instance, if I say a set of prime numbers, what are prime numbers? You know that prime numbers are numbers that cannot be divided. Okay, so we have gone on to define a set as a collection, or a well-defined collection of items or objects. Now, let me quickly state that a set is usually represented, okay, by this symbol, this symbol. And then when we talk about the elements of a set, we are talking about those items, okay, that are within that set. Those items that comprise the set. Those items that make up that set. For instance, if I say that a set of prime numbers between 1 and 20. I'm talking about those prime numbers within that range. What is a prime number? A prime number, of course, you know, is a number that can only be divided by 1 and itself without a remainder. If any other number divides it, there will be a remainder. So A prime number is a number that when divided by any other number, there will be a remainder, except by 1 and itself. So 2 is a prime number, 3 is a prime number, 5 is a prime number, 7 is a prime number. Okay, the next prime number is 13, right? The next one is 17, and then 19, right? So now, if we represent a set by this symbol, we begin, okay? Prime numbers, okay? We can say that we can represent the prime numbers by P. So we would say P, which is our set, is equal to, that's how we do it. So we say 2, 3, 5, 7. 9 is not a prime number, sorry, because 3 can divide 9. So we say 11 is a prime number. Come on. 11 is a prime number. 11, 13, 14, 15, 16, 17, right? And finally 19. Okay? And then we close. So that's how it goes. A set of fishes in River Niger. And what would we be talking about? Maybe herrings, scumbia, right? Is it scubia? Well, herrings, tilapia, titus, shark, whale, you know. And of course, always remember to close the objects or items within the symbol as we have here, and then your set is complete. Good. Now we will talk about the elements, the number of elements in a set. The number of elements in a set. There are times, okay, when a set may well be talking about certain numbers that would repeat themselves, okay? So the number of elements in a set are the total numbers of the elements represented in the set. However, if a number is repeated, whether once, whether twice, thrice, or even 10 times, as many times as possible that a number may be repeated, that number will always be counted as 1. Okay, what are the now in this set P? What is the number of the elements in this set? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that is represented with N, okay, of P, and we say it is equal to 8. N stands for number. Number of elements in set P is equal to 8. Okay, now if, for instance, we had any reason to repeat 5, and maybe a reason to repeat 3, and maybe a reason to repeat 7, okay? Of course, you would see that we have added 1, 2, 3 elements into this set P, and that would have brought the total individual elements to 8 plus 3, right? And that would give us 11. But the total number of elements in this set P still remains 8. The reason is because no new number has been introduced into the set P. All the numbers here are the same numbers that were there when we indicated the number of elements as 8. So it does not matter how many times a number repeats itself in the set. What matters is the number of elements that were never repeated. You see? So whether we have 2 repeating itself, 3 repeating itself, 7 repeating itself, it doesn't matter as long as the numbers are still the same. Now we proceed. Elements of a set and number of elements in a set. Please let me quickly indicate that the elements of a set is usually represented by the symbol, by this symbol, okay? And here it is important to put your set in brackets. Now we will proceed to look at subset. Subset. A subset is the set in a set. Simply put, subset. The set in a set. Now every set is a subset of itself. That's one thing you must note. And a null set, okay, is also a subset of any set. What is a subset? What is a null set? A null set is a set that is empty, okay? It has nothing inside of it. So it is that null set that is, or that set that is empty, is a subset of any set, or a subset of a set. And also the full set is equally, that is, a set that is filled is equally a subset of that particular set. I'll explain what I mean. Don't get confused. Okay, so let us assume that we have a set A. And it contains the elements 1, 2, 3, 4, and 5. Then we have another set, B, and it contains the elements 2, 3. Now look at this. 2 and 3 are the elements of the set B. Now 1, 2, 3, 4, 5 are the elements of the set A. But if you look closely, you will realize that 2 and 3 are also in the set A. So it's more like we have just gone on to pull out the numbers 2 and 3 to form another set. And we pulled the numbers 2 and 3 out of A, or set A, to form set B. So this set B is a set in the set A. So B is a subset of set A. Is that clear? Now That is how a subset works. But like I said, that every set is a subset of itself. That is to say that, for instance, let us consider the set A. If we want to look at the subsets of A, for instance, that would be too much. So let us stick with B. Okay? Let us stick with B. You know, they usually say that teachers will give their students the long ones. Yes, because you have more time. When I don't want you to play around, I give you assignment. Well, for now, let us consider the set. Okay? Let us consider B as a set on its own. Now, how many elements do we have in this set B? We have 2 elements. And like I said, if we were to break down, okay, I don't want to confuse you. Let's take another set, okay? I will call the set that I'm about to take now, I will call it set X. And set X will contain the elements 7 and 9. Good. Now, this is a new set, X, with the elements 7 and 9. What are the subsets of this set, X? Let's list it together. The first is, you see those brackets as they are, or the enclosure you have there is in itself a set. So we are gradually moving to what I call the power set. You will understand. Now the next element, or the next subset, is 7. The next is what? 9. And the last is 7 and 9. Now, how many subsets do we have out of set X? This is 1, 2, 3, 4. Good. Now, from this set X, we have 4 sets evolve, or rather 4 subsets evolving. So, the power set is the total number of subsets, okay, that can be evolved, or that can evolve from a particular set. Does that make sense? Okay, let's put it this way. The number of subsets which a particular set has is called its power set. The number of subsets which a particular set has is called what? Its power set. So, for every set that has 2 elements in it, the power set is what? 2 raised to the power of 2. If the set is just 1, for instance, we are going to have sorry about using just a bracket. We are going to have how many subsets? The first is the null set, okay, the empty set, and the second is what? The 7. That is 2. So if it is one element in the set, the power set, this is the power set is what? 2 raised to the power 1. Similarly, if there are 3 elements in that set, the power set will be what? 2 raised to the power 3. If there are 4 elements, the power set will be what? 2 raised to the power 4. 5 elements, 5 raised, 2 raised to the power 5. And so on and on and on. Okay? Now, with this we come to the definitions, okay, of sets. We will now go on to look at the types of sets. So now let's quickly look at the types of set. Types of sets. We have the empty set, we have the finite, the infinite, the disjoint, and the equal sets. When we talk about empty set, we talk about also the null set. We've already talked about that, right? And we said it is represented by this symbol. It's a set with nothing inside it. It is empty, null. Another way to represent it is this. Good. The finite set. Finite means tickly, small, not endless. Okay, finite means it can be counted. So when you say a set is finite, it means that the set can be counted. It may take long, fine, but you can count it. For instance, if I say the number of grains of rice, or the number of rice grains in a bag of beans, is finite, right? You may take 4 days to count it, okay, but you will definitely reach an end, because you're not counting the grains of beans. If you just pour the beans over on the floor, you can actually spot the grains of rice that are there, and you can count it fine, right? Okay. And if I say the number the boys or students, the students in your class, you can count them. Maybe as I'm even talking now, you can begin to call out their names: Funke, Fumi, Tolu, Ngozi, and you can quickly go on to count them, right? So that's finite set. You can count it to the end. But infinite set is uncountable. Infinite set is uncountable. For instance, if I say multiples of 9, multiples of 3, multiples of 2, oh my God, you will count to zillion, trillion, zillion. Okay, you will still be counting. So it's infinite. You can't reach the end, okay, of that set. You can't reach the end. So we say that set is infinite. And then disjoint set. Disjoint set talks about two sets, okay? Disjoint set talks about two sets that have totally different elements in them. For instance, if I say that set A is equal to 1, 2, 3, and I close it, sorry, that symbol. All right, and I say that set B is of course, you can see that set A and set B, they have nothing in common. They have absolutely nothing in common. So, when two sets have nothing in common, we say they are what? They are disjoint. However, when set X and Y are considered as 7, 8, 9, and then set Y, okay, set X 7, 8, 9, and set Y is, for instance, 8, 9, 7. You can see that all the elements in X have been repeated in Y. It does not matter the arrangement or rearrangement of the elements in that set. What matters is that 7 is here, 7 is here, 8 is here, 8 is here, 9 is here, and 9 is also here. And so we simply say that set X is equal to set 9. But here set A is not equal to set B. Okay? They are disjoint. So that's what we mean, okay, by equal sets and disjoint sets. Again, null set or empty set, finite set, infinite set, disjoint set, and equal set. Now, we talked about subsets. Okay? Let me quickly bring to your notice that subset has the symbol like this. It's not C, okay? It's actually deeper than a C. Okay, so that's the symbol for subset, just to bring to your notice. Then we will proceed without wasting time to the relationships between sets. Now, when we talk about relationships between sets, two things quickly come to mind. They are intersection and union of sets. Intersection of a set is represented like this. Union of a set is represented the other way around. This is not an N, this is not a U, okay? But the N, or rather the one that looks like the N, stands for intersection, and the one that looks like the U represents the union. Now, intersection of a set simply means that particular set, okay, that indicates the elements that are repeated in two sets. Now this is what we mean. For instance, you have set A to be equal to, okay, 1, 2, 3, 4. And you have set B to be equal to 2, 3, 4, 5. Okay, let's end it there. Now the intersection, okay, the intersection of set A and B will simply be what? 2, 3, 4, right? Because now 2, 3, 4 is in A, and 2, 3, 4 are also repeated in B. So A intersection B will be equal to 2, 3, 4. Does that make sense? And then when we talk about union, union is the combination of all the elements in A and B, okay, without repetition. Without repetition. Now, what do we mean? Look at A. A has 1, 2, 3, 4. B has 2, 3, 4, 5. Now, union of the sets will combine the elements in A and combine the elements in B without repeating any particular element. So, A union B will be equal to 1, 2, 3, 4, and 5. We are not going to say 1, 2, 2, 3, 3, 4, 4, 5. No, we don't do that. We simply write out the elements as they are without repeating any one. And that is A union B. Now, the next thing we may want to look at is the universal set. The universal set. Universal sets are often indicated or enclosed within a triangle. That's when we talk about Venn diagrams. So we'll get there very soon. Now, the universal set is the complete range of elements, okay, of a set from which other sets that is from which other subsets are derived. Universal set, okay, is a complete range of the sets or all the elements to be considered from which other subsets may be derived. For instance, the universal set, okay, universal set. The universal set is represented by U or okay, this Greek alphabet. You can also use U to represent the universal set, either of the two. Now, let us, for instance, say that the universal set we are considering is all of the integers between 1 and 10, okay, 10 inclusive. For instance, if I say that the universal set is the set of X such that X is all the elements of the natural numbers, okay, and then x being okay, let's say natural numbers, x being greater than or equal to 1 but less than or equal to 10. Now the universal set of x such that x, okay, is the number or the total number of elements, okay, or the total number of natural numbers, the total elements of natural numbers, such that x is greater than or equal to 1 but less than or equal to 10. Definitely our universal set will be something like this. We'll be talking of all the elements from 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now we have the universal set, a universal set like this. Now we can have what we call the complement of a set. Let's say this is our universal set, okay. Now we have another set. Let's call that set P, and the set P simply is maybe we can say the prime numbers, okay, the prime numbers such that the prime numbers, okay, less than 10, prime numbers less than 10, of course we'll be talking about 2, 3, 5, and 7. Good. Now we can see that all the elements in set P are also in the universal set. However, complement of set P which is represented as P prime or PC, okay, P to the power C, complement of set P, okay, will be all the elements that are in the universal set, okay, that are not in P. So if we are considering the universal set and the element P, we would simply say that the complement of set P is what? 1, 4, 6, 8, 9, and 10. Does that make sense? It sure should. So prime, okay, complement of a set is simply those elements in that particular set being considered that are in the universal set, okay, but are not in the set being considered. Complement of set P are all the elements in the universal set that are not in the set P. I hope that is clear enough. Now let us quickly look at the difference of sets. Difference of sets when we consider two sets. The difference of the two sets are the elements in A. Okay, if we consider two sets A and B, for instance, so we say the elements that are the difference, okay, between set A and B are the elements in set A that are not repeated in B. And then when we consider the difference of sets, okay, of the difference of set B with respect to A, we say the elements that are in B that are not in A. Now, difference of sets is usually represented by A minus B. That is for sets A and B. If it is set X, Y, of course it will be X minus Y. Okay, so for instance, if we have set A to be equal to A, B, C, D, E, and we have set B to be equal to A, C, E, F, maybe G. Now, difference of set A with respect to B will be those elements, okay, that are in A but are not in B. We have B is in A, okay, we have D is also in A. Now these two elements B and D are not in set B, right? B and D, they are not in set B. However, they are in set A. So that is, we say set A minus B is equal to B and D. We can also have B minus A. That is, those elements that are in B but are not in A. What are the elements there? We have F and we have G. It's as simple as that. Okay, so with this explanation, we will now go on to Venn diagrams. Venn diagrams. Venn diagram is used usually to represent complex problems on sets. The Venn diagram was invented by an English mathematician by the name John Venn in the year 1834. Okay, John Venn lived between 1834 and 1923. Okay, so it was within this period that he invented the Venn diagram. The Venn diagram is usually represented by rectangle and oval shaped circles. That is, in the Venn diagram you see things like this. The rectangle represents, well, I hope this looks like a rectangle. The rectangle represents the universal set, while the oval shaped circles represent the subsets Okay, so in the Venn diagram you see something like this. The rectangle, okay, for instance, represents the universal set, and the oval shaped circles, they represent the subsets of the Venn diagram. Okay, we have a question on the board, and the question will be solved using Venn diagrams. However, before we solve it, let us get a grip of what Venn diagrams is all about. These are various representations of Venn diagrams. We have subsets P and Q. Okay? In this very representation, the shaded portion of these two subsets is the point of intersection of the two subsets. And that point of intersection, we represent it as P intersection Q. In the second diagram here, if you can clearly recall the complement of a set, in the complement of a set, we said that the complement of a set is that all the elements of a particular set that are not represented in the universal set, okay, all the elements of a subset that are not represented in the universal set. So all of these places, or all of this is subset Q, okay, and everything else that is within the intersection of P and Q, okay, that are not represented in P. We can represent this Venn diagram like this: P minus Q. That is the set or subset P minus the set Q. It can also be represented as P intersection Q prime or Q complement. In the same way, all the elements in Q that are not represented in P, we can further represent this situation as Q intersection P prime. In this case, all these two sets or two subsets are shaded. So this is P union Q. In this portion or in this place, we can see that both subsets are apart from each other and none of them have been shaded. And so we call this a disjoint set. There are other cases, okay? There are other cases in which you can have three subsets. For instance, you can have the subsets P, Q, and R. If the intersection of the three subsets are shaded, it will be represented as P intersection Q intersection R. Okay. There can be another case where only the portion where P and Q intersects are shaded. In this case, we can represent it as P P intersection Q intersection R prime. R prime simply means the elements in R that are not represented in the intersection. So we will now go on having a knowledge of what Venn diagram is about. We'll go on to solve our problem, okay? The Venn diagram will begin by drawing our rectangle which represents the universal set. And our universal set here is 40 students. We have the Hausa speaking. We have the Hausa speaking students. We have the Igbo speaking. And we have the Yoruba speaking. Okay? Now, before we go on, let's read the question. In a class of 40 students, 25 speak Hausa, 16 speak Igbo, and 21 speak Yoruba. Each of the students speak at least one of the three languages. If 8 speak Hausa and Igbo, 11 speak Hausa and Yoruba, and 6 speak Igbo and Yoruba, draw a Venn diagram to represent the information using X to represent the number of students who speak all three languages. Calculate X. Okay? Now, X, they said, we should use to represent the number of students who speak all three languages. And the number of students who speak all three languages will be at the intersection of Hausa speaking, Igbo speaking, and our Yoruba speaking students. Okay? Now, the next, if you're going to solve a problem like this to save yourself of a lot of headaches, begin in the middle and then to the other intersections before you go to the outer part. And I tell you, your problem will be few. Okay, so we now go to the second part of the question, which tells us that 8 students speak Hausa and Igbo. Where is the intersection for Hausa and Igbo? That's here. So 8 speak Hausa and Igbo. At that intersection, you always remember to remove that which has already been placed in the center or in the intersection of the three subsets. Then 11 speak Hausa and Yoruba. This is the portion for Hausa and Yoruba speaking students, and we're told that 11 students speak Hausa and Yoruba. And the other intersection for Igbo and Yoruba, we're told that only 6 speak Igbo and Yoruba. Of course, always remember to remove your X, which is at the intersection of the three. And then here at the outermost part, we are going to move up to the first portion of the question, which says 25 speak Hausa, 16 Igbo, and 21 Yoruba. Okay, where is Hausa? This is the Hausa speaking students. Okay, and remember, since there are 25 of them who speak Hausa, we will simply remember to remove this 8 and 11, which we were told also speak Hausa and Igbo, and also they speak Hausa and Yoruba, and then we'll add our X. So if we add 8 and 11, that will give us 19. 25 minus 19, that will be 6 plus X. 6 plus X. Now that is the number of students who speak the Hausa language. Okay? Alone there. The next, we were told that 11, okay, we were told that 16 speak Igbo. This is Igbo. Okay? And out of that 16, already 8 speak Hausa and Igbo, and 6 speak Yoruba and Igbo. So that's 6 and 8. Okay, that gives us 14. So we are left with 2. Of course, you add your X. And then the last part is the Yoruba speaking. We're told there are 21. If you add 11 and 6, that would give you 17. 21 minus 17, that's 4. Of course, remember to add your X. Now, just in case you are wondering how we came about these figures here, I will explain. Remember that we have been told that 25 students speak Hausa, 16 students speak Igbo, and 21 students speak Yoruba. Now, if we take the Hausa speaking students, for instance, okay, we have been told that 25 of them speak Hausa, and out of that 25, we will remove the number of students who already, okay, speak these languages, and or the number of students who speak other languages, for us to get the number of students who speak only Hausa, and that will give us 25 minus 8 minus X plus this X plus 11 minus X. Is that not so? Okay, because we will remove all these who speak Igbo, Hausa, Igbo, Yoruba, and Hausa and Yoruba. We will remove them from the number of students who, students who speak the language in general, and we have been told that the number is 25. So when we remove the number who speak the combinations of other languages from 25, we are going to have, of course, minus X, okay, we're going to have, if you open up those brackets, or rather, you can see minus X and plus X will go, okay, and then we have, this becomes 25 minus, okay, 8 plus 11 will give us 19 minus X, not so. If we open up those brackets, we will have 25 minus 19 plus X. 25 minus 19 is what? 6 plus X. Yes. This is how we got our 6 plus X here. If you did that same with Igbo, you get your 2 plus X. If you did that also with Yoruba, you will get your 4 plus X. It's that simple. Okay? Another very brilliant and easy way to do it is you simply add up 8, the figures that you know, you add them up, 8 and 11. Okay, that will give you 19. That is this 19 here. So you remove 19 from 25, you get 6. And then since in the intersections okay, of two languages, you already have minus. Where you have only one language, you use plus. As simple as that. And then, if we have done that, and our Venn diagram is ready, our question is as good as solved. Okay, so now we will go on to add everything and equate it to 40. And when we do that, we begin with the students who speak only one language. Then we proceed to the students who speak two languages. And then we end with the students who speak all three languages. And so we say 6 plus x plus 2 plus x plus 4 plus x plus 8 minus x plus 11 minus x plus 6 minus x plus x equal to 40. Okay? We have 6, 8, 10, 18, 29, 18, yes, 29 and 35. Let's get it right. This is 2, this is 8. Oh, this is 12, sorry. 8, 6, 8, 12, 20, 21, 37. So we have 37, okay. Plus x goes with minus x, plus x goes with minus x, plus x goes with minus x. So we are left with only one x equal to 40. And so x becomes equal to 40 minus 37. Our x is what? 3. So we've been told to calculate x. Now we know that only 3 students out of 40 students speak all 3 languages. Now, with that, we come to the end of Venn diagrams. In this topic, we've looked at definitions, types, relationships between sets. We've looked at universal sets, the complement of a set. We've looked at the difference of sets. We've also looked at Venn diagrams, and we've solved problems using the Venn diagrams. Now, a couple of questions will pop up on your screen. Do well to attempt them. And if you have any questions, please feel free to replay the video. Thank you.